Hi, very good morning. So, today we are going to look at the second module, chapter 1, class 12 physics. So, last day we learned, in the last module we learned about charges and electrostatic force between the charges and field existing and electric field intensity at any point near a charge. And then we learned about electric dipole, and electric dipole is actually an equal and opposite charge separated by two equal and opposite charges separated by a finite distance L. And the strength of the electric field, electric dipole, the strength of the electric dipole can be measured by a parameter called electric dipole moment, which is P is equal to the distance into one of the charge, and the direction is P cap. The direction P cap is actually from negative to positive, so this is the direction of electric dipole moment. So these are the arbitrary और इजी तरीके से लिया जाने वाला एक डायरेक्शन है, एक कन्वेंशन है ये, और पॉजिटिव नेगेटिव भी हो सकता था, नेगेटिव टू पॉजिटिव भी हो सकता था, बट वी हैव टू टेक ए डायरेक्शन. अगर इफ वी आर गोइंग अप एंड वी आर टेकिंग द अपवर्ड डायरेक्शन पॉजिटिव, then downward direction is negative. That is a similar way. From negative to positive, we have fixed the direction of electric dipole moment as P cap. So today we are going to derive electric field at any point on the axial line, on the axis where the dipole lies, on the axis of the dipole. So this is called the axis of the dipole, and at any point, a point here, a point here, whatever, at any point, wherever, but on the axis of the dipole, we are going to find how much is the electric field. So let's start the derivation. So we'll draw an dipole for the purpose of understanding and keeping it a large distance, but it is a very small finite distance. And distance between these two charges I'm going to take as 2a. Even I can take a simple L, A, whatever, but I'm taking 2a's for easy derivation. You can take simply A also. And the center of the dipole is somewhere here, and the distance from the center is A, and the distance from the center is A. So I'm going to draw the axis of the dipole, and I'm going to take any arbitrary point. Suppose point A somewhere here, and at a distance x from the center of the dipole, and distance x from the center of the dipole. So first of all, let's write the dipole moment. Electric dipole moment is equal to distance into one of the charge. The direction is P cap, and the direction is negative to positive. That is a P cap. So this is electric dipole moment of the given dipole, and we are going to find out the electric field at point A due to this dipole. So for that, we can go for individual charges. The plus Q is producing an electric field at A, and minus Q is also producing electric field at A. So electric field at A due to, so electric field at A we are going to find. The first is electric field at A due to plus Q charge. So for a point charge, the electric field is 1 upon 4 by epsilon naught Q upon the distance. What is the distance from plus Q to A? From here to here it is x, means from center to A, and here to here is A, so the distance is x plus A. So the formula is electric field is equal to 1 upon 4 pi epsilon naught q upon r square. So r square, instead of r square we have x plus a square. And the direction is, for a positive charge the electric field line is, for a positive charge what is electric field line? Electric field line is always outwards. So I am going to put the charge electric field direction in this way, outwards. So this is the direction of electric field due to plus q. So this direction is the p cap direction. You see what is the direction of p cap? This is the direction of p cap and this is the direction. So both the directions are just opposite. So I will write here the direction is minus p cap, because for a vector quantity you can't simply algebraically add or subtract vector quantities. You have to go for the direction and you have to use the vector laws to add. So this is E due to plus q charge at A, and E due to minus electric field due to minus q charge at A is 1 upon 4 pi epsilon naught q upon x minus a the whole square. Why x minus a the whole square? Because from the center to A is x, from the center to minus q is a, so from here to here is only x minus a, this distance. And the direction will be plus p cap, because for a negative charge the electric field line is entering. So here this will be E minus due to minus q, but the direction is in the same direction of p cap, so plus p cap is the direction. So now you see the directions are just opposite, so you just subtract it. If something is going up, something is going down, yes, something is plus 5 and another is minus 3, so you can simply, even algebraically you can do here, because it is just opposite direction. If they are at some other angle, then you have to go for the components. But here, there is no requirement of any components here, so we can simply add electric field at A is equal to this sum of these two ones, and something is common here, 1 upon 4 pi epsilon naught q. So in the bracket you will get 1 upon x minus a the whole square. I am putting it first because this is positive and this is negative, so the negative one I am putting after. And again rest right p cap. So p cap is also common, but I am writing p cap at the end because it shows the direction. So 1 upon 4 pi epsilon naught into q into, what about this? You have to calculate this. So in order to calculate this, take the LCM, x minus a the whole square into x plus a the whole square. And this side you will get x plus a the whole square minus x minus a the whole square. So the rest of the derivation is just the algebraic calculation of this. So I am going to do the algebraic calculation. So I am going to wrap it off. So the algebraic calculation is E at A is equal to 1 upon 4 pi epsilon naught into q. So I'm going to expand these two formulas using a plus b the whole square and a minus b the whole square. So a plus b the whole square is a square plus b square plus 2ab minus a square plus b square minus 2ab divided by, and here also I can write it like this, x minus a into x minus a, or x plus a into x plus a. And instead of doing a long calculation, I am going for a short calculation here in the denominator. So the numerator, a lot of things will cancel. X square plus a square plus 2xa minus x square minus a square minus minus plus 2xa divided by, and I am going to pair this 1 plus and 1 minus. X minus a into x plus a is x square minus a square and this is also x square minus a square. P cap is a direction, so 1 upon 4 pi epsilon naught into q, and you're getting, you can cancel these x squares and a squares. 2xa plus 2xa is 4xa divided by x square minus a square, the whole square p cap. And here in the beginning we have already written p is equal to 2aq p cap. So is there any 2aq in the numerator? I can write this numerator as 2aq into 2x divided by x square minus a square, the whole square. So the final answer is 1 upon 4 pi epsilon naught, which is a constant k, into 2x upon x square minus a square, the whole square, into p, vector p. So for easy calculations, we are going to do some approximations, and the approximation is this. These two charges are very close because the distance are very less in micrometer or nanometer or angstrom. So the a is very smaller than x. So a is much smaller than x. So we can neglect a square. So the final answer is 1 upon 4 pi epsilon naught 2x p cap divided by x square cos square is x to the power 4. So again the calculation will give you x4 over x, 2p cap upon x cube, 2p vector upon x cube, where p is the electric dipole moment, or more in short form if you want to write, you can write it like this, 2 kp upon x cube, where k is 1 upon 4 pi epsilon naught electrostatic constant. So it is purely depending on the electric dipole moment, which is again a constant, and 1 upon cube of, or inverse of the cube of the distance from the center of the dipole. So if you go for x, a graph of E versus x, you will get a graph like this. 1 upon x, 1 upon x square, 1 upon x cube will always have the similar graph, but the slope will increase. Okay, so that's the final answer for electric field at any point on the axis of an electric dipole. So the next topic, the next derivation is electric field at any point on the equatorial plane of an electric dipole. So what is our electric field equatorial plane? So for that I am going to draw a diagram, plus q minus q. So this is electric dipole, and the distance is again 2a. So from the center, one is a and other one is also a. So a plane passing through the equatorial plane. It's not a line, it's a plane, a paper. A plane passing through the center of the dipole, perpendicular to the electric dipole, is actually called equatorial plane. So we are going to find any point. So electric field due to a dipole, electric dipole, at any point on equatorial plane. So at this point, what is the electric field intensity? So for that, again, from the center of the dipole, the distance we will take x, and we'll find the electric field at A due to plus q charge. So again, the formula is 1 upon 4 pi epsilon naught q upon r square. So plus q upon distance. So from this q to this point A, what is the distance? This is the distance. So this distance can be calculated by Pythagoras theorem, because this is 90 degree. So by Pythagoras theorem, this will be under root x square plus a square. So the distance is under root x square plus a square, the whole square, because r square is a distance formula here, q upon r square. And the direction is very quite difficult direction, because minus q2 plus q, the direction is this, p cap, direction of electric dipole moment. But this direction is from positive charge, this will be the direction, because outward direction. So this direction we cannot compare it with this direction, because this is at an angle and but this is just horizontal. So here we have to go for components. So I am writing only the magnitude now, and if you take the direction you have to write by some symbols and say along BA, that's the direction, along BA. In the same way, what about E minus Q at A? 1 upon 4 pi epsilon naught Q upon, here also the same thing, this is the distance, under root x square plus a square by Pythagoras theorem. And along, what is direction? Because for negative charge, the direction is to inwards. Inwards means this is the direction of E minus Q. Along AC, not CA, but AC. So the magnitudes are the same. So I am going to consider this magnitude as E. So this is E along BA and this is E along AC. I am going to take the components here. So if a vector is somewhere like this, what can be the component? Go for the Cartesian coordinate system. So I'm going to draw it somewhere here properly. So we have a force like this and another force like this, E plus Q and E minus Q. And I'm going to take this as the origin and x-axis and y-axis. So if the magnitude of this is E, then this will be something like E cos theta, and this will be E sin theta. And for this also, if you take this as theta, then again this is E cos theta and this will be E sin theta. So there will be two vertical components which are cancelling, but two horizontal components which are not cancelling, which are in the same direction, so they will add. So here we can say that the vertical components cancel. Vertical components cancel each other, and the horizontal components add up. So the total electric field at A will be 2E cos theta. But which direction? This direction. So this direction is actually the opposite of P cap. So we will write minus P cap. It's the direction. But how come this both are theta? Suppose this is theta, then I can write this is also theta, because corresponding angles. If this is theta, this is also theta, because for an isosceles triangle, equatorial plane actually equal distance from here. So it is isosceles triangle. For an isosceles triangle, if the opposite angles are actually equal, the sides opposite equal angles are equal. So this is theta, then this is also theta, interior alternate angles. So both are theta, so E cos theta, E cos theta. So they are equals. So now we will go for finding, we already know what is the value of E and we'll put the value of E. And then we have to put the value of cos theta and finalize the answer. So let's do that. What is cos theta first? From this any triangle you can find cos theta. Cos theta is, sin theta is perpendicular upon hypotenuse and cos theta is base upon hypotenuse. So base. So for this theta that touches is a base, or hypotenuse we already know, under root x square plus a square. So we are going to put this value over here. So I'm going to rub it off. So E at A is equal to 2E is 1 upon 4 pi epsilon naught K Q upon R square. Q upon R square is x square plus A square. Cos theta is A upon under root x square plus A square, or P cap minus P cap is the direction. So E at A is equal to 2 into, so don't cancel this 4 because this is surface a constant. So let us keep the constant as it is, because 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9. So here becomes it becomes what, 1 upon 4 pi epsilon naught, let me put this 2aq together, 2aq p cap together, and the minus is the whole answer, divided by x square plus a square the whole raised to 3 by 2. Why it is 3 by 2? Because this power is 1 and this power is 1 by 2. So 1 or 1 by 2, it will become 2 1s are 2 plus 1, 3 by 2. That's the power, how we calculate. So here also we can go for the approximation. Anyway, this is the answer, or we can even write this answer in electric dipole moment form. Vector P, because 2aq p cap is electric dipole moment, x square plus a square the whole raised to 3 by 2. But if a is much less than x, because a is distance between the charges, which is actually very less, very small quantity, so we get 1 upon 4 pi epsilon naught p upon x cube, as x square is negligible. Sorry, a square is negligible. And the final answer is A is equal to minus kp upon x cube. So the last answer you might have listened very carefully. The last answer was what? My plus 2 kp upon x cube, and here minus kp upon x cube. So the directions are totally different, and plus minus difference is there because one is along the direction of electric dipole moment in the axial line, or in the axis of the dipole. Always the direction is along the dipole moment, electric field direction, and in the equatorial plane the direction is always opposite to the dipole moment, and the magnitude is actually half of what is on the axis. So that's all about the derivation part here. And let's go for the next topic. So the next topic, before entering into the next topic, so last day I gave you an exercise 1 point in the last module, 1.1 to 1.7, but in this you have to go for 1.8 to 1.40. So 7 more questions to do, so that we can revise and you can understand it numerically. So this is a homework for you. Size 1.8 to 1.4. 14. Okay. Now, one more topic I will just teach and finish this module, and that is, if you keep this electric dipole in an external electric field. So there is an already electric field existing here. I am going to depict that electric field by parallel lines. This electric field is due to maybe so many positive charges and so many negative charge here. So you can easily understand, if there are so many positive charge here, then the electric field will arise like this, and so many negative charges here, the electric field will always enter into the negative charge. So let's go with a uniform electric field. So electric dipole in a uniform electric field. So in a uniform electric field, how this dipole behaves? So for example, let's keep a dipole here at any orientation. So these are simply field, I am showing field lines, imaginary lines, but this is an actual dipole. So external field, this is uniform external field, means every point it has a particular value, and that value is E. So what is a force acting on the dipole? Net force acting. So for that I am going again for the individual dipole, individual electric charges. So what is the force on minus Q? What is the force on plus Q? Always negative charge will experience a force in the opposite direction of electric field, and the positive charge will experience a force in the direction of electric field, because of the formula that we already know, F is equal to Q into E. That's the relation between F and E, force and electric field. So if the Q is positive, so it has the same direction, and if the Q is negative, then the direction is like this. So the direction is negative. So a negative charge will always experience a force in this direction, and a positive charge will experience a force in this direction. So the net force is very simple. The net force is 0, because both are equal and opposite. They cancel. But there is a torque acting here. There is a torque acting on the electric dipole. So how much is the torque acting? Is the torque cancelling? So for a torque, you can see this is a dipole, and I am applying a force like this, so it will go down, and this will go up. And if I apply a force like this, you see, still it is going up. So the direction is same. It has a clockwise rotation. So if there is a force like this, it has a clockwise rotation. A force like this. You see, I am applying a force like this. It will go down. And if I have a force like this, still it goes down. This part goes down. So it goes anti-clockwise, clockwise, and here also it goes clockwise. You see here, again I am showing it. Clockwise, still clockwise. So both have same direction, so it will not cancel. Opposite direction cancel. So in the torque we can write it like this. The torque is equal to R perpendicular. R cross F, that is actually the formula for torque. Or you can even write R perpendicular into F, the magnitude, or R tau is equal to R into F perpendicular. So the magnitude you can easily find by perpendicular distance and force, or perpendicular force and distance. So we'll go for perpendicular distance and force. So the torque is perpendicular distance. So this one is 2a. So this is what is the direction of electric dipole? Minus P2 plus minus Q2 plus Q. The direction of electric field is this. So it has an angle theta between P and E. So there is an angle theta between dipole moment and electric field. So the torque can be written like this, R. So what is R here? If I take this as the axis of rotation, when it rotates, so this will be A, and this is a perpendicular distance. So perpendicular distance will be so let's take the perpendicular distance. This is a point and this is a force. So a point and a force. What is the perpendicular distance between this point and the force? This one. Okay, so this is not a perpendicular distance, this one is a perpendicular distance, which is can be calculated by sine theta is equal to perpendicular upon hypotenuse. So perpendicular is equal to A sine theta. So the perpendicular distance is A sine theta into F. In the same way, for the next one, plus Q charge also, this A sine theta into F. So this will be 2A F sine theta. 2A and F is equal to QE sine theta. 2AQ is P, so P is sine theta, where P is electric dipole moment. Magnitude of electric dipole moment. So in vector notation, if you write, you will get P cross E. The torque acting is P cross E, and the magnitude is PE sine theta, where theta is the angle between the dipole moment direction and electric field direction. So today we are concluding this module at this topic. When you keep a electric dipole in an external electric field, it will not run away or it will move, it will not undergo translatory motion. It will not go from one place to another. Rather, it will just rotate due to this torque. And it will not go anywhere because the net force is 0. But the electric field must be uniform. So your homework again, I am reminding you 1.8 to 1.14. So do this questions so you will be able to revise the topic that we have learned.